Very soon, close.
That's dedication.
Low carbon footprint.
This is most stupid. And then Australia.
You want to wait or could we start?
Well, there are other people who start at 10:30. Remember, they have a timetable.
10:30.
They may be taking a coffee break at 10:30. You've got a minute.
Say something
So then I can.
Now remember what I wanted to say. Please take your valuables, your laptop, your wallet, that sort of thing with you, because I can't close this door, and although it's unlikely, not impossible, somebody comes in and grab the laptop. So please take it with you to tea time and lunch, and you can put it there in that DJ gallery. That's the only thing I wanted to say. Also, tomorrow I think I will find a microphone that we then have to run around and talk to people who ask questions, but because we're going to be in a slightly bigger room just next door to host that can take more people.
So next two talks are going to be very interesting because they're going to be presenting some opposite opinions. So the first talk on Bushveld field observation is coming from Bushveld's own Rais Latypov. So, Rais?
Okay, good morning, everyone. So you see the title, final title of my talk, Magmatic Dropstones in the UG2, UG1 sequence. And let me start with a short kind of introduction into dropstones. I just came from the DAI conference in Morocco, and there were a lot of crazy people talking about the dropstones. And I show them the stuff I'm going to show you. They say, okay, you need to call it magmatic dropstones, your stuff. I said, okay, I'm buying your suggestion. And that's how the title finally came. So what's something is not, what is important about these dropstones, I mean, sedimentary, you know, that is a major feature of the glacial deposits. So when iceberg comes into ocean sea, it's melted, and these debris melted out, and they settle to the chamber, in this case, not to the ocean sea, and they impact the sedimentary rocks. And when they do this, so we have they deform the sediments, still downward, and then they are draped over by sediments from above. And you see these nice, to the right, you see this nice two example of dropstones from the from Namibia, nicely show how they impact these layers. And two things which is important to stress here for my today talk is that there is a sharp interface here between the top of the pile and the dropstones, which are released from the iceberg and falling on the floor, sharp boundary, and then the fact that they deform this layering. And if they deform, so apparently these black guys already existed on the floor to be deformed like that. So it's impact and deform what already exists there. So that is a story that people get out of the dropstones, because apart from many other things. But of course, now it's moving or not, doesn't want to move for some reason. Again, some problem. And I thought that we, in magmatic systems, okay, now it works. In magmatic system, actually, we also have dropstones, and I suggested now to call them magmatic dropstones, and they have a different name. They called included blocks, cognate inclusion, ortholis, something like that. And of course, the pioneer here is Neil Irwin, and that paper, which you can see here, it's absolutely, from my point of view, absolutely masterpieces, absolutely must-read paper. Not easy to read, but a lot of information, a lot of interesting geological observations. And that's his story when roof is broken and these ortholis, they are falling to the chamber floor and deforming the layering, which is at the base, something like that. You see these blocks, which on the example of the blocks, and his story is that if you have such kind of blocks and it's it's falling on the chamber floor and deforming this layering, it means that the boundary between the cumulate part and magma was sharp, absolutely sharp, and the layering was already here. Layering was already here. And we see this with many blocks in his paper, and especially this one. And that is not a result of this deformation, also important to stress, it's not a result of compaction or something like that. It's because you see that below that block, on that side, there's no any deformation. So it is draping over. So layering is draping over the blocks. And unfortunately, I've never been to the Skaergård. Still my dream to get there, but fortunately, I've been to the Duke Island, another famous intrusion studied by Neil Irwin, and that is where we really have a fantastic example of dropstones, and just massive dropstones, which are falling from the roof and deforming the layering like that. Again, suggesting that when this drop is falling, then you're deforming the layering already there, and the boundary is sharp. And that's one of my favorite example. If you just kind of get your eyes there, you see that is a block. It's a big block which fell from the roof, and you see that layering, it is kind of folded. What's happened here, according to the Irwin, and I agree with him, that the falling block kind of knifed into the flue comet and redeposited these layers on the right. Again, suggesting and stressing repeatedly by Irwin that all layering is forming at the crystalline face. It's already there when the blocks are falling on the chamber floor. Okay, so let's now go to the Bushveld complex and let's see how these ideas may help us to get the idea about the formation of the chromitites in the Bushveld complex. So you see the big, as you know, there's the biggest magma chamber in the world, growing from the base, mostly from the base upwards. And one of the important features of the Bushveld complex and many other complexes, maybe 99% of the complex actually, there's no roof sequence, which is quite strange because mostly cooling happens from the roof, and you're supposed to have a roof, but we don't have them. And the reason, most likely reason, that at some point, roof of many of these complexes, apart from maybe Skaergård and Kiglapate intrusions, which survive, actually they just collapsed, and these blocks are falling on the chamber floor. We recently discovered such kind of blocks in the Sudbury complex, for example, big blocks, kilometer size. And I think the same story happens with the Bushveld complex. And if it happens, so we're supposed to see these blocks of the roof rocks on the floor sequence. And that is testable idea. Now I'll show you what we are calling a dropstones in our case. We found them, I think, and very nice examples. And this is how they look like. This is UG2. UG2 sequence, and the blocks are indicated by, you see this, where they have 4 blocks, and that is a slide where you're supposed to say, wow, because that's what I said when I first saw these outcrops. And let me summarize some of the major features of these blocks. So first of all, these are fine grains. What are they? They are fine grain to medium grain melanite orthopyroxenite, texture dissimilar to the rocks, surrounding rocks. So there's a not kind of in situ rocks here, except if we look at the description, we have a kind of in old literature, they called brown sugar narites. The blocks, the lenses described as a lenses in the Myrensky Reef. I now strongly suspect that that is the same thing. These are the same blocks. And these blocks have the rims, as you can see nicely in these blocks, which are sitting, we discovered this block in the MG2 sequence, deforming the MG2 sequence, and quite distinct. So you can really see in the field if it's what? No, that's fine. I will try to show here. And you see this rim. And composition, as I said, that is texture, that is a fine grain finely melanorites with 20% of MgO. So it's really different from the surrounding rocks, pyroxenites, not the pyroxenites. Then in terms of size, very different size, and from centimeter to meters, and some of the most spectacular tabular blocks up to, at least I've seen 10 meters, and I suspect that maybe much bigger blocks. That's how they look like. One of the blocks, the size you can see here, and that is another block, and you see the me as a scale. So there's about 15 meters or so, big blocks of kind of foreign rocks sitting here in the UG1 sequence. And magma cannot really bring such kind of big blocks in the chamber. That's physically, I think, impossible. And there was, I think, the most likely these blocks must have been derived from above. So that dislodged from the magma, dislodged from the roof sequence, just in the way Neil is proposed for the Skjergård intrusion. And what else? Yes, and occurrence of the block. All these blocks which we found, they confine to the sequence of the host rocks of these massive chromitites. So UG1, UG2, MG2, and I suppose the Myrensky as well. So they really confine to these sequences. And just to show you, that's example of the one of the trench. And you see these blocks. These are these dropstones, and that's, we go to the map, and you saw this blocks, UG1 chromitites, and orthopyroxenite above, and norite below, and the blocks are all with chromitites, telling us that the event which produced chromitites somehow produced these xenoliths, these blocks which I suspect falling from the roof. So that was tectonic event which produced these blocks, and then that's why they are together with the chromitites. Okay, let's go to the most important part now, to the field relationships of the blocks and the chromitite layers. The first feature which I like to stress is that angular blocks, they disrupt igneous layering in the chromitite sequence, just in the way they do this in the Skjergård intrusions. And that's one of the my favorite example of the blocks, large blocks of these melanorites sitting in UG2 chromitites, and you see that it's disrupted these at the top of these UG1. There was anothersites on both sides and continuous, and the slacking here was disrupted. And I'm not entirely sure about these chromitites which are above. Either they were also disrupted because there was oblique impact, so that they were deformed, or they were deposited later. I'm not yet sure, but the fact that this block disrupted the layering tell us that the layering was already here at the time of this block fell on the chamber floor. Another examples, that is a block. Sometimes you need really to get your eyes to see these blocks. Again, these anothersites on both sides, this layer is disrupted by this block. Another lenticular type of the block, this part is important to look, where we see that the chromitites layers are truncated by this side of the blocks. Of course, to be truncated, they should be already there when then the blocks is falling, saying that chromitites already there at the time of these blocks, when time of the blocks was falling on the chamber floor. Feature 2 is the angular blocks which indent chromitite layers beneath and are covered by planar layer from above. That is series of blocks. That's one of my favorite here. You see nicely that these blocks indent the chromitite layer. It's substantially thinner here below the blocks, telling that, again, deformation of the chromitites, which should be here at the time of this block falling. And at the top, a little bit complicated because there is a reverse fault here. But still, if you look, that is the chromitites above. You see that it's not deformed at all. That was slide prepared for the Alan Wilson. Alan Boudreau, unfortunately, he didn't come today because we were discussing this time, and he was talking about the compaction. But such kind of relationship definitely tells that's no compaction, because we deforming the chromitites, but nothing happens at the top. So the layering above is not really deformed around this block. And there's a special story why this not happens. It's a very interesting story, actually. And another big blocks, not actually big, but angular, which you see the deforming, the impacting and deforming chromitites, UG1 chromitites. And actually relationship is the same as was described by Neil Irwin. The bigger blocks, there's no relation that the bigger blocks really disrupt the layering. What is important is the shape of the block. If it's angular, it deforms. If it's tabular, it may not deform the layering. It's just sitting nicely on the top of the layering. And that is the cases where it's really disrupting. That's another blocks sitting here in the UG1 sequence with the chromitites, which are again indented. You see that they're deformed below the blocks, and even layering and orthosite layering is deformed and much thinner below the blocks. So it's squeezing the anorthosites here. And at the top, the layering is planar, and perhaps you don't see that there's a smaller chromitites layer, which is also not deformed. Again, no indication that there's no compaction in this case. And that's also included this block yesterday just to show how nicely this layering below the chromitite deforms. Apparently, blocks was falling this direct, was impacting the layering from that direction. And the final feature, the chromitites and silica, they are draping over the blocks with or without deformation of the rocks. That's outcrops, and these are blocks. These red one are blocks, UG1 sequence, and this one, so sitting in another side, chromitites are not just here again, stressing that these dropstone only with the chromitites, not no below, at least not above in this case. Unfortunately, the rocks, we don't see rocks below. And if we come closer here, getting closer, then we see that the chromitites below blocks are not deformed. I think that because they were really solid, almost solid. So the blocks cannot really deform them. That the ones, the further ones which are depositing on the top, they are deformed above these blocks. So that is a story from that slide. That's another example, the same. So we see these blocks, which again is not able to deform the layering below the blocks. It's not able when indenting, but because the layering above is deformed here. Interestingly, just one thing I would like to draw attention, look at this on the other side, what happens? How thick is this and how almost disappearing here? Not entirely sure what that means, but I would like stressing because the next slide showing us another example of the block where it's totally different situation. We see this layering above the blocks, and it's absolutely the same thickness of the anorthosites and basically chromite, maybe a little bit thinner on the top. Not yet sure what does this tell us, still thinking about these relationships. And the base is straight, is planar, absolutely planar. Another example of the UG2 chromitites. And from the distance, you wouldn't even say that this is UG2. That's really unusual one, because usually with anorthosites, etc., but that is not at all. And this is block and sitting, and you see that the chromitites are developing above the block. We have several other, and when they came later, and when this block was already moved, we saw that there is actually a layer below the block, which is also deformed by this block. That's example of block in the UG2 sequence, doing basically the same thing. And the last few slides, just showing development of chromitites above and below the blocks. That is a block, chromitites indented chromitite below, and the one with draping over above. That's another example of the same relationships. That's another example of the blocks doing the same thing, and that's even clear without any boundaries. And I think that's my last one, which is the big blocks here sitting just right on the top of UG1 sequence. And you see that the sequence of the chromitites is substantially increased because we're just adding the block here. That's why thickness is increasing in this area. Okay, so what is our implications for the origin of chromitites in the Bushveld complex? This conclusion actually not that far from what Erwin concluded, basically strongly influenced by Erwin, but Erwin was talking about the layering, simply layering, while I talking about the origin of chromitites, which are part of the layering which we observe below these blocks. So there was almost invariably sharp interface between the top of the cumulate pile and of the critical zone and the main body of overlying resident melt. So we're talking about the hot chamber floor, which was indented by these falling blocks. The uppermost part of the cumulate pile was coherent, at least 50 maybe % of the crystallines, or maybe perhaps 90-95. That's what we were talking about this at the conference. And igneous layering involving UG1, UG2 chromitites were generally fully developed right up to the crystal lignin phase. So the chromitites were there already at the very top at the time of the falling these blocks. When blocks landed on the chamber floor, chromitite layers were already there, yeah, and in direct contact with overlying resident melt, because otherwise you cannot really indent them. And chromitites were formed by deposition of chromite crystal directly onto the chamber floor. So chromitite was directly, my data, this set of data doesn't tell whether it was in situ crystallization, gravity settling. This data doesn't tell us, but they were deposited as whatever process directly on the chamber floor. And such a deposition of chromite crystals alone on the chamber floor implies that the resident melt in the chamber was saturated chromite alone. There was no any other crystals. Otherwise, they will be really involved here. So we need just magma which crystallized chromite only and nothing else, and depositing on the chamber floor. If to summarize in a cartoon, which I always like to draw a cartoon, so then we have something like that. We have a magma in the chamber saturated chromite only, and chromites at the very top forming from this magma, then blocks is falling from above and indenting the layering, chromitites, including chromitites. Then because magma is saturated, still saturated chromite, then chromites is growing further and draping over these blocks. The same basically chromitites. And then finally, we have other layering above, and at some point this layering just moved out and becomes planar again. So that's, I think, where, from my point of view, this field observation take us. And I think very important constraints, field-based constraints on the origin of the chromitites. So take-home message, UG2, MG massive chromitites, and where there's places where we found these dropstones, were likely produced through the deposition of chromite crystal directly on the chamber floor, from the overlying resident melt saturated in chromite alone. And one thing which, unfortunately, James is not here. We had James Dren, we had a nice discussion about these experiments which he done, and we really learn a lot from each other about his experiment and my data. And I just would like to mention this to kind of indicate some points here. So why melt was really saturated in chromites? So in our model, which was discussed today by James, the magma comes and due to pressure change, it becomes saturated chromite and crystallizing chromite. That was because of the topology of the diagram. We have so-called chromite trough. Basically idea, and that's what I would like to mention here, that's if we have something like that, and with a decrease of pressure, the volume of plagioclase is increasing. Just look at this yellow field, it's increasing. Then inevitably all this diagram moves to the left, and this red point, which is there, it's standing on the same place, and it becomes saturated in chromite. So basically in our model, we're talking about the shifting of the field of the chromitites, so that magma comes into the field of chromite. And what is the experiments, I got finally from the James why his magma becomes saturated in chromite. It's not in the paper, and I don't know, he preferred to talk about the solubility. I don't understand these things. For me, the diagram is much better to show in the diagram what's happened in the phase diagram. Finally, I got it from him after long discussion. So what really happens that if we take this kind of Niels diagrams, you have a pressure at high pressure, solubility at this point, and which X here, and then low pressure, and low pressure it is over there. So it's basically we're talking about the increase when he says that solubility decreases. That means that the volume of olivine increases. So that's the eclectic moves right side, and here it is. So that and for this reason, basically magma becomes saturated in chromite. So just because of increasing the volume of the chromite field. In paper, he is arguing about something taken about the chromite content in OPX on the right side. Yes, at high pressure, we have a high chromium content. At the lower pressure, we have lower content, chromium content in OPX. Some argue that that has importance for the chromite. I'm not convinced at all for this. I think that still, if we're looking at this like the diagrams, what happens is just with a low pressure, with a change of pressure, you're just shifting and irrespective how much chromium you have really in OPX, you're just shifting the diagrams and the liquid becomes saturated in chromite. But irrespective of our disagreement, we fail to convince each other in these things. But irrespective of that, we both agree that whether this is a shift of chromium field, as in my model, or that is the expansion of chromite field, doesn't matter. It happens just with the pressure, with a decrease in pressure, and magma becomes saturated in chromite and may do the job which we would like, I would like it to do. And I think that's it from my. Thank you very much. Yeah.
Why are the blocks only enclosed in chromite layer, not in other layer?
Sorry, once again.
Why are these blocks only enclosed in chromite layer?
Yeah, okay. Yeah, because I think this is because the origin of chromitite layers are related with the replenishment of the magma chamber with new pulses. And that's also tectonic. There's always tectonics when you bring magma into the chamber so that it shakes the magma chamber and the blocks are falling from the roof at that time. And when we have then slow crystallization, they stay there where they are. And next time when you bring magma and you shake it again, blocks falling. So it's like kind of coincidence. They don't really responsible for the formation of chromitites as well. They just add to the story, tectonic story.
Hello.
Yes, Johan.
When your block falls down.
Yeah.
It's also it's the bottom is actually you are sitting on a plagioclase in many of these. The plagioclase chromite codectic. So in fact, it's not just chromite that is getting this block story. The plagioclase, the identical story is happening to the plagioclase as well. So it's actually not just a chromite story, it's a plagioclase or an orthosite and chromite story. And in other places, it's a pyroxenite and chromite story.
Yeah, well, whatever we have in the magma chamber at that time, and see whatever layer is sitting on chamber floor, yeah, that's effective. We deform basically, we deform chromitites, we deform an orthosite, whatever is there, and whatever. Yeah.
Add to that. So when you're saying that the layers are not deformed, you have to look at the plagioclase. Chromites won't deform. They're tiny blobs that can literally like a little balls move around when this falls.
I'm not talking, when I say deformation, I'm talking about the entire layer, and we see they're deformed.
Yeah, but you
what-
said, did you say that some things is not deformed?
No, it depends on the situation. There are cases where the blocks are falling and they're deforming the chromitites below them, right? And then they making it thinner, and that's where your story comes with a compaction perhaps, and you're squeezing that guy.
So you could actually test if you go back on your layers on your blobs that are surrounded on both sides.
Yeah.
It might be discriminatory, it might not, but if you see deformation in plagioclase, I would never expect in a chromite. If you see that the plagioclase is deformed below,
Yeah.
but not above, then you can say, okay, this was still kind of soft, it can have been formed. Whereas
Yeah, it can be added. Yes, I agree.
I think that plagioclase is actually very important.
Textural observation will certainly help. We are not yet at that stage. We have the samples, so we can look at this. But you know, when I talk about deformation, I'm talking about what I see in by my eyes in the field. I think that's.
I just want to pick out that it looks like some of these thick, longish blocks that in fact the entire succession is kind of a little bit squished up, so it's reduced in thickness.
Yeah, maybe.
In
Yeah.
some cases, so that means that you actually have to expel liquid from.
Yeah. In some. Yeah. We have a mushy stuff. Tomorrow I'm going to talk in the morning. So we upper part is still mushy, so we can squeeze it and make it thinner. Yeah. I'm quite perfect with this.
You said you mentioned that these dropstones occurring predominantly associated with the chromatites.
Yeah.
But do you have examples where you've seen this happen for the Mariinsky as well?
Not yet, but I said that these blocks, they were described in the Mariinsky Reef as brown sugar narites, and I strongly suspect that these are the same blocks. But nobody, you know, to see that you need to be lucky really to have that outcrops. In chroma, for Mariinsky, we don't have such beautiful outcrops. To see that they are blocks, that's why when they see in underground, when you're sweating like a hell, you know, and you want just think how to get out of the mine, you know, you don't really think about whether it's block or whatever. So that's lenses and that's it. But you need really to be lucky to see them in the field and nicely exposed and weathered. That's where the story becomes finally. So we have it in the landscape, but we don't see them. We don't document them yet. Let's say.
I have actually kind of two questions. The second one is the general, but the first is that why the blocks are so fine grained. That's interesting. And the second one that you described that you know the upper part of the intros have collapsed and we have blocks there, but then you described that kilobyte and scarebyte are an example that we have preserved upper part. So what is that? Is it something to do with the shape or the size of the intro?
Yeah, that's a thing which I'm working now. I can tell you that So the fine grain, short answer, I don't know. I'm thinking about that. The point is that they are different from the surrounding rock. That was very important because that is, we have a in situ, I described earlier, in situ remnants of the paraxenite, and they're absolutely the same. So that is different. These are something different. I don't know why they're fine grains. In terms of the roof, these two intrusions, Kiglapate and the Skergat, they have basalt on the top, and I think that is the key. The roof is stick to the basalts, and they stay there. They cannot be disrupted. In most intrusions, they have counter rocks, sedimentary counter rocks, which are melted, and that is a dead end for the roof. It's collapsed because of melting of the roof. That's my kind of idea. Maybe there's better explanation. I don't know.
First.
Yes, Steve.
Yeah, just a question about possible sample bias. So you've shown that the blocks are associated with chromites, but of course that's where most people look. I mean, that's where the interesting rocks are. Is there a possibility that there are actually blocks distributed to the rest of the sequence? That
Yeah, I think there is a possibility. We've done our best to go up and down, of course. And then the problem that in paraxenite, if you have such kind of block in chromitites, you can definitely see this. When this guy is sitting in the paraxenite, it's not that easy to see. But we're done on our best, we don't see it. But you know, we have other examples. We have anorthosite blocks, we have paraxenitic blocks, real paraxenitic in other sequence in the main zone. So they are falling. They're falling from the roof, from my point of view. And bias, yes, but at least on that kind, we see that the most of them sitting with, and there's no reason why it shouldn't fall when, you know, we still have shaking, maybe not that big one.
There was one question off here.
Rais, do you have
Yeah.
any compositional information to suggest that these rocks are in fact related to the Bushveld complex? Are they Bushveld complex rocks? Could they be
Yeah, no chemistry, but we have one block found one block which in the central part has a paraxenite, normal paraxenitic texture. So that's why I'm guessing that these are recrystallization, the kind of hornfels, because we have now the blocks which preserve this original in the central part, kind of the untouched. But it would be nice, yes, to do isotopic strontium isotope test to prove that they really belong to the Bushveld. But for my story, it doesn't really matter. It may be even quartz blocks. The major thing is that they're falling, they're deforming the layering, in this case chromitites, and that tell us that chromites are formed at the chamber floor. So that's my story basically. And I don't care about the origin of blocks at this point. Yeah. Thank you.
Just one.
Oh yeah.
One,
Sorry,
one little comment.
what if you kill me?
No, I will.
You will. Okay. Thank you.
Thanks, Zoya. Thanks, Zoya. Nobody needs to join from outside. Doesn't look like it. I don't know how Zoom works, so. Mate, does anybody want to join? No. Okay, good, excellent. Yeah, so somewhat related to Rais's talk, I will talk about Bushveld chromitites and with somewhat different interpretations, but we are Bushveld chromitites. Firstly, great that Chris was talking about Stillwater, because one of the differences between Stillwater and Bushveld is that in the Bushveld, our chromitites do not normally sit right at the base. They sit here in the critical zone, 500 to a kilometer above the base. At Stillwater, 500 meters to a kilometer above the base, at Stillwater, we have chromitites right at the base of the intrusion, which is something that we've been puzzling at Stillwater, actually, what the reason for that could be. And Jim Mangel talked about the assimilation of banded iron formation. That was really interesting because Stillwater complex essentially is in contact with banded iron formation along almost its entire width. And so it's possible that the assimilation, you disagree, Chris? Certainly there's banded iron formation. Anyway, so this is an interesting possibility that the stratigraphic low position of Stillwater chromitite is related to the assimilation of banded iron formation. We can talk about that, Chris. He's shaking his hands, so We're a bit worried. So here we are. These are the Bushveld chromitites in the critical zone, lower and upper critical zone. And this is a plot showing you the modal abundances of minerals. So red is olivine, gray is orthopyroxene, white is plagioclase. And you can see that the base of the upper critical zone is where we have the first significant layer of plagioclase-rich rocks and an orthosite, in fact, that defines the base between the lower and the upper critical zone. So in this talk, I will talk about chromitites layers particularly occurring in the upper critical zone and right at the base of the upper critical zone where they're associated with an orthosite, because I want to talk about the origin of chromitites and anorthosites. I feel they are very closely related. And I will look at the classical locality here at Jachtlust, the farm Jachtlust, where Merensky worked, and Wager and Cameron and so on and so forth, where we have a Cameron section, the classic exposure. And then I will also compare that to chromitites in the Western Bushveld, that Union section, where we have only drill core data. In the West, we have very little outcrop compared to the East. So in the West, we depend on drill core data. And then also I will show some pictures here from Smoky Hills Mine to compare that. All right, so I think we can skip about that quickly. Next year is a field workshop in the Bushveld complex at Wits University, 100-year anniversary of Merensky's discovery of the PG reefs. And I hope many of you will come to Wits, and we will certainly have an excursion. I'm sure Rais will organize one excursion here to Cameron section. This is it, where we have a complete exposure of lower zone, fully exposed here because they're olivine rich, so they erode very effectively. Lower zone or hardspogites and dunnites with orthopyroxenite layers that stick out a bit more here, less erodible, they dip towards the center. And then here, plagioclase begins to appear, and there's the boundary between the lower and upper critical zone. And this is where the famous, this is Cameron section, and this is the key outcrops that I'm going to show you now in this talk. And there's also a poster upstairs where I show some of these pictures. So this is the MG3 chromitite at Jachtlust. First on the left, and this is it at Tweefontein, about 50 kilometers further south, or 70 kilometers. As you can see, the stratigraphy we think is broadly similar. We have an anorthosite, the first anorthosite here appearing in the sequence, defining the base of the upper critical zone at Jachtlust and at Tweefontein here. The chromitites have markedly thicker at Tweefontein than they are at Jachtlust. This is a difference, and in fact some people wonder whether indeed we can correlate these things along strike. But anyway, let's assume we can, and so I'm going to focus on this chromitite and this underlying anorthosite. And there's another chromitite here at the base, which I'm also going to briefly talk about. So let's look at this chromitite here, at this chromitite in particular first in detail. There it is. And so as you can see here, this seam, when you look at it in detail, and it's very well exposed, people have looked at this thing for 100 years, literally, student groups, and so on and so forth. And the one thing that really strikes you when you look at this is there are many similarities, at least superficially and initially, and I would argue probably also more pervasively, to sedimentary rocks, sedimentary mass flows. Okay, we have features here that we find in sedimentary mass flows. Flame structures, we have graded bedding in places, not always, but in places. Here towards the top, we have banding, we have all sorts of otolith fragments. Maybe that's what Rais thinks are these roof fragments, these roof blocks falling down. But they, of course, there are anorthosites, there are pyroxenites, they are basically the roof rocks and the floor rocks to this chromitite seams, what we find here, except that the anorthosites seem to be a bit purer. The chromitites warp over the otolith. They do, in fact. Sometimes the otoliths indent the floor rocks, suggesting compaction, I think, although Rais thinks there is no compaction. So lots of variability here and lots of indication, to my mind, of sedimentary mass flows. This is what Wordsworth, I think 50 years ago now, said. He compared these things to sediments and called them magmatic sediments. All right? And so, you know, I'm not saying anything new here. The old guys, the old timers, they have figured these things out already, long time ago. What else? Oh, yeah. So you can also see chromitite fragments or otoliths, and I will suggest to call these things actually fragments. I mean, people have suggested these things are fissures, comparable, you know, things that occur in metamorphic rocks, but I think we probably better call them fragments of chromitite here in the anorthositic floor rock, and we find anorthosite fragments in the pyroxenitic roof rocks. So I think this is important. There are incipient boulders. It appears that it appears that the chromitite seam here is beginning to be dismembered into this sort of Boudin shapes. Note also that some of the otoliths are tiled. So there is an otolith above another otolith, and this seems to be wrapped around it somehow. Again, something that we find in sedimentary mass flows. I hope there are some sedimentologists amongst you who will be able to argue with me. I'm sure that can be argued because I really know very little about sedimentary rocks. And then let's look at it in even more detail. Here, some of these fragments, these pyroxenitic fragments, they are rimmed by chromite. And I know that Brian is going to talk about this in a lot, so I'm not going to steal his thunder, or only a little bit, maybe, because, you know, I mean, one of the arguments that Rais in the past 10 years is always making about in situ crystallization, I think, is these overturned chromitite stringers around potholed Merensky Reef. And he says that's impossible to do by gravitational settling of chromite crystals onto the top of a cumulate pile. But here, clearly, of course, we're not talking about, you know, chromite crystals growing in situ on top of a cumulate pile. This is clearly a late stage feature, these chromite rims around these otoliths, as I'm sure Brian will explain in more detail. And Roger Schoon has talked about this a lot too. So, you know, what else? Yeah. So again, you see these lots of these little lensoid fragments and schlieren of chromite in the chromite seam and then also in the underlying anorthosite. Another thing that I notice is that when you look at this fragment here, and again, it's a tiled fragment with an anorthosite closely associated with it, just below, is that you have chromite concentrations in what you might call pressure shadows here and here at the end of this fragment. And so this, one could argue, is also a sedimentary feature. When we have a flow of a chromite-rich slurry or mush and chromite being concentrated in these sort of pressure shadows. I'm sure I'm using the wrong term, but there you go. So, you know, to my mind, lots of evidence for sedimentary features. But on the other hand, one could also argue that these things indicate, what's the structural geology term, that they essentially indicate solid state deformation in a ductile regime. What was it that Tom Blenkinsop called these things?
Soft sediment.
No, not soft sediment. Anyway, it'll come back to me. So yeah, so here is Rice's argument, you know, about these chromitite stringers that overturned the Merensky Reef potholes, arguing that these things represent in situ crystallization of chromite. I couldn't disagree stronger. Another thing, by the way, that is interesting here, it's a picture from Rice's very interesting papers. And you see here the apophysis of the Merensky Reef injecting into the floor in a sill-like manner and surrounded by a chromite stringer, and then also an anorthosite rim, corona. I come back to this. I think this is typical and very important also in understanding these things. All right, there we go again. Look at this thing. This is a PhD student for me who now works in the oil industry, went over to the dark side, very successful, very rich. So in Australia. But yeah, so there is another chromitite stringer here at the bottom, you see, and it's an undulating one. People have called this an egg box-like texture. It's undulating, and we have similar egg box-like chromitite stringers in many other layered intrusions. Rum is a classic example. Brian and Rice have described these things in the past in lots of detail, and other people also. So we have these quite commonly. I'll show you another example from another layer in a moment. And people have wondered about these things. And when you look at this thing in more detail now, then this is how it looks like at the base. Same outcrop at Cameron section. So there is your underlying pyroxenite, the chromitite stringer, a couple of millimeters, sometimes a bit thicker here. There are some places where it bulges up a little bit. It has a rim, a corona of pure anorthosite right on top of it. And in places when you follow it here, you see the chromitite goes up a little bit and the corona follows it quite reliably. And to my mind, this is a reaction feature. The anorthosite is a reaction feature. What's happening to my mind is, and this could be, before I come to the model, let me show another example of this. This is what we call the pseudo-reefs in the Bushveld complex. This is ultramafic layers, quite pegmatoidal in places that look like Merensky Reef, but they're much less mineralized. That's why we call them the pseudo-reefs. And they occur stratigraphically a few tens of meters below the Merensky Reef. And they are ultramafic layers that are rimmed by chromitite stringers at the bottom and at the top, as you can see here, undulating again, and sometimes very, very strongly undulating. And in many places, they are directly overlain by an anorthosite that then progressively turns into a monoritic, leuconoritic material here. So a pure anorthosite. Okay, so an analogy to the MG3 seam that we just saw a moment ago, where the anorthosite occurred below, here it's occurring on top and below. To my mind, what this indicates is that the pseudoreefs came in as a sill, partially melted the noritic host rocks, left an anorthositic restite behind. We can model these things, and people have modeled these things on melts, that we can do this. And so to my mind, what's happening here is the B1 magma, perhaps crystal bearing, perhaps a slurry already, perhaps even with some chromite phenocryst, as Jim Mangel argues, intrudes into a leuconoritic sequence. It partially melts the leuconorite, produces an anorthosite. The partial melt of the leuconorite is aluminium rich. It reacts with the B1 magma and produces a thin chromatite stringer. I think nothing of this is new. It's been proposed by people for many other intrusions before. And the question then, of course, is why the undulating nature? The undulating nature, to my mind, is simply a result of relatively late stage deformation. That's something Zoya might want to test at some stage. So the whole package, of course, is in a subsiding crustal package, very dense, 10 kilometer thick intrusion. The whole crust is subsiding. These ultramafic layers, if they come in late, they probably undergo some flow towards the center of the intrusion, and their contacts are slightly moving and undulating. I don't have, any constraint or proof for this at the moment. This is my suspicion, and I suggest people can test this with EBSD, for example. All right, yeah, and sills. So I suggest these things come in as sills. Okay, and people, again, there are people who strongly are opposed to the concept of sills. Jim Mangel was, I guess, one of the first to propose sills based on geochronology, and I'm not arguing that this geochronology is very enigmatic and we don't understand it. Nevertheless, the field evidence, I think, tells us that their sills must occur, and Rice does actually concur with that. This is from Rice's paper here, a beautiful example of Merensky reef forming sills injecting into the floor of the reef itself. And there, by the way, is the pseudoreef, the top of the pseudoreef Harzburgite that we just looked at before. All right, but let's go back to the MG3 footwall anorthosite, back to these lenses, these little fleeren and lenses of chromite in the anorthosite, in the footwall anorthosite. So I'm a little bit doubtful. I mentioned that these things perhaps could be magmatic sediments, mass flows. But the other possibility, as I said, is that this is a solid state ductile flow, penetrative deformation. This is, I think, what Tom Blake is. Of course, you can see that I'm not very good in structural geology, but this is the other possibility, that all these things are moving hot shear-like, in a hot shear. Everything is deforming, largely solid, but it's still moving, perhaps because of the subsiding Bushveld complex towards the center, or perhaps into local depressions and large, super large potholes. These things can be kilometers across and deep. So everything is moving, and while everything is moving, it's deforming like this. This is something we need to test. We can test probably. There you go. The UG1 footwall, the UG1 chromitite in places at our Mandelbrot mine, it looks like this underground. So intense disturbance and dismemberment of the chromitite. And you see exactly the same little lenses that we saw underneath the MG3, right? And then in places, what it does here, the MG3 and its footwall anorthosite, when you go along strike, here, it begins to sort of mingle, the anorthosite and the overlying pyroxenite begin to intermingle, and the anorthosite is spreading out, becomes thinner, lots of thinner layers that thin along strike. There we still have these fragments here, dropstones. I don't think so. Across this thing, sometimes you can even see some evidence, perhaps some folding here. You see, I think this is probably a fold hinge going through here, and Jean Bedard in Bay of Islands has shown us examples that these things occur there too. I think we have quite much more folding in these packages than we think, often generating isoclinal folding, so that we have anorthosite layer, bands of anorthosite layers that, rather than representing two different layers, represent simply two limbs of a fold. In places, then these things become so dismembered that we just turn it into little lenses and schlieren like this, you see? This is happening actually in the hanging wall of the MG3, chromitite and anorthosite lenses and schlieren. You go along strike, they become smaller and smaller and ultimately turn into this here. A finely layered banded pyroxenite with occasionally still a few of these dropstones sitting in it, but almost unrecognizable. And then in places, this is from the UG2. Here you see we have these long meter-like, sometimes 3 meter long otoliths. Very thin, very long. this cannot be sedimentary mass flows. I think this has to be, ductile solid state deformation of material while the whole thing is flowing towards the center of the intrusion. Now, I would say this cannot be a dropstone. This has to be penetrative deformation of material while everything is flowing. And, when you go to the interval there at Cameron section, you find all sorts of evidence of intense deformation, rotation, folding, schlieren, and so on and so forth. So my model then in summary for this is that we had originally here a noritic interval, perhaps leuconoritic. We have a magma influx on top of the crystal pile, perhaps. That would be the Mg3 chromitite that precipitates from this magma influx. It could also be a sill, I can't tell, but anyway, a new influx of magma precipitating Mg3 chromitite and pyroxenite on top of it. We're undergoing mass flow, sorting this slurry, concentrating the chromite to form the chromitite seam. It locally injects into the floor rock. Anorthosite fragments are included, are entrained into this slurry and sitting in the chromitite itself. We undergo partial melting of the underlying leuconorite to produce the pure anorthosite, and everything is continuing to move. Okay, and then the next thing that happens is we have a new magma influx, and this must come in as a sill, I think, to produce this thin chromitite stringer on top of the pyroxenite that's sitting in the Mg3 footwall. So I think the evidence for me, to me, is that we have here certainly evidence for sill-like injection of magmas into this package. We have evidence for mass flow, sedimentary mass flow, but we also have evidence for penetrative deformation. I think we are right at the transition between the sedimentary regime and the solid state regime. So both are happening in the same outcrop often. This is what's confusing us. That's what's been confusing us. Several processes happening in the formation of ore deposits, not just one, and often in the same outcrop. This is what has been and keeps on confusing us. And finally, just a few pictures here now from Union section in the West drill core, where we only have drill core data to study this sequence really. And this is from Bernd Teigler's PhD and his sample. So we are now here at the Mg4. Again, in the upper critical zone, the Mg4 is underlain by, as you can see, anorthosite, banded anorthosite with leuconorite. And then further down, another interval here of banded anorthosite leuconorite, that's the Mg4A. Here's the Mg4. Between the Mg4, there is an unnamed chromitite interval, very thin, stringery. Again, it's sitting on anorthosite. Not a coincidence, I think. Then below the Mg4, we're coming to the Mg3. We just looked at that. There it is. It's sitting on anorthosite. And in this case, in the West, actually, it's not the footwall to the anorthosite is not pyroxenite, it's actually norite here. And the chromitite stringer is lacking in this place. But we have these little fragments here, dropstones, maybe, of pyroxenite sitting in there. And they're UG1. UG1 pyroxenite. Rais showed lots of images of this. Pyroxenite sitting on anorthosite, and the anorthosite is intensely banded, lensoid, schlieren-like, anorthosite fragments and lenses. Chromitite fragments and lenses in the anorthosite. So this, of course, this is the classic exposure. So yeah, so this is, I argue here that this is not a coincidence that chromitites and anorthosites are very closely associated, spatially. They form by the same kind of mechanism. They related to each other. Chromitite forms by new influxes of B1 magma precipitating chromite and pyroxene, and then granular flow separates chromite and pyroxene to produce pure chromitites and pyroxenites. And the underlying norite is partially molten due to the heat flux from the new influx. And the chromitite, therefore, in places sinks into the underlying anorthosite. It collapses into it. And I will show now a few pictures from, do I still have time, a few minutes? I will now show a few pictures here from another place in the Eastern Bushveld complex at Smoky Hills mine, Mandosuk, actually the discovery site of where Merensky discovered the PG reefs, where I can show you that evidence that the chromitite collapses into the anorthosite. And also I will show you evidence, and this is where I argued with Steve yesterday, I will show you evidence that the anorthosite actually injects into chromitite and locally possibly erodes the chromitite. So this is Smoky Hills mine. We have this amazing, strange pothole, large pothole of anorthosite. So we do have potholes not just of pyroxenite, we have potholes of anorthosite too. And I come back to the origin of possibly that in a moment. But here, this anorthosite pothole cuts the UG2 sits down here, and here is the UG3. You see, this is one of the samples that Steve imaged yesterday with this beautiful Maya mapper technique. And there's another part of the UG3. The UG3 really consists of two seams, and there is actually a thin chromitite stringer right at the contact between the UG2 or 3 pyroxenite and this anorthosite, a thin, laterally extremely consistent chromitite stringer that is just 2 millimeters thick. All right, so this is what I'm going to want to look at in particular here, this anorthosite below the UG3. You see this one here, and it actually seems to link up to that pothole, but I'm not going to talk about that. And there it is again, the same anorthosite here below the UG3. Let's look at it in a little bit more detail. There it is, somewhere here now. We are somewhere here. There it is. And I think you would argue with me, you would not disagree with me, that this seems to suggest injection of the anorthosite into the chromitite. Now, how on earth can you inject material that is monomineralic? How can anorthosite flow? This is something I will discuss in a moment, but let's first look at the evidence here, at the field evidence. So the anorthosite seems to inject into the overlying UG3 chromitite. There are some more pictures on the other side of the pothole. Here is again the UG3. There's the anorthosite. See how it suddenly blows up? It blows out, it expands underneath and above. It forms sort of a blowout, a big bulge of anorthosite that has these apophyses here seemingly injecting into the pyroxenite, continues here and becomes thinner again, like typical. And notice here that the chromitite, the UG3 chromitite, actually begins to collapse into the underlying anorthosite here. And I'll show you the detailed picture. Here it is. There's the UG3, and it collapses down into the anorthosite. The detailed relationships here, what's happening is not entirely clear. We are not allowed to go to this face because it's very dangerous, it's very steep. So we had to take the photograph from distance, unfortunately. We can't map this face in detail. So, but certainly there's evidence that the anorthosite, that I think you would agree with me, is intrusive, that the chromitite is collapsing down into this in large rafts and fragments into the anorthosite. The anorthosite also, and this comes from somewhere down here, you see lots of thin leuconorite anorthosite bands here in pyroxenite down here. And when you look at those in detail, you see that they also show evidence in I think quite clearly of deformation of solid state, I would argue perhaps in this case, or ductile deformation. We're forming these little sort of, what are they called, apophyses or extensions that indicate the direction of the movement here, of the flow, of the solid state flow in all these little layers. Locally, they turn into little lenses. This is exactly what we see in the MG3 footwall and elsewhere. These little lenses and fragments of anorthosite, they are the result of the disintegration and dismemberment of these more coherent seams here. Okay. We see evidence of movement of intrusion of anorthosite in many places in the Bushveld and in other layered intrusions. Marion has shown an example from Skaergaard yesterday, and here is a one from the Moimesis from Eastern Bushveld complex, where a lot below the pyroxenite marker, anorthosite, model anorthosite, seems to inject into the overlying layered interval of melanorite. This is Marion showed an example of this from Skaergaard, I think it was, where she argued, we form an anorthosite here by liquid immiscibility of something more mafic, a more mafic melt, leaving behind an anorthosite. And I think, this may be the stuff that Rais was talking about too, these sort of sugar, brown sugar norite or something. And so I think what's happening here is that Marian's idea, that we have liquid immiscibility may well be the evidence for it. We're producing here anorthositic or very leucocratic noritic material by removal of these relatively mafic melts that inject into the floor here. You can see that locally quite nicely. They form these little plumes here. And in fact, when we go back to that at Smoky Hills, that thick anorthosite that also locally forms the big pothole, then this thick anorthosite is really crisscrossed with these, they called IRAPs. They are iron-rich, ultramafic pipe-like bodies. And I think these things may represent the residual melt that's draining out of anorthosites, leaving behind, of norites and gluconorites, to leave anorthositic restites behind here. This is how they look. You see, they seem to be percolating downwards, although, of course, this is just a 2D image, so there seems to almost move upwards here. And you have all these sorts of shapes. They are closely associated with this anorthositic band and then seem to pond here against the pyroxenite in places. Yeah, so basically that's it. That's just a picture from the upper zone showing you again that many of the magnetite seams are also associated very closely with anorthosite. Grant Cawthorne made this point years ago. Here, a main magnetite seam overlying anorthosite, having lots of anorthositic rafts, otoliths, and fragments in it, often lens-like. This is a picture from, I think, Moline, 1970s or 60s. You know, these little lens-like otoliths, same as things as we find in the MG3. And a little plume here. I'm not going to talk about. That's it. Thank you. Questions?
Yeah, I think that there was this one very beautiful cartoon that you showed that the magma influx there. So then you said about the slurries. So at which stage the magma influx turns to slurry? I mean, that does bring the crystals, the magma influx, or
Yeah.
just immediately begin to.
Yeah. So yeah. A lot of debate again on that has over the years, you know, Jim Mangel, for example, argues that these magmas, and Hugh Eales also years ago already argued these magmas come as slurries already in training, lots of crystals and chromite, and I think Yao with Jim has the same kind of model. I couldn't disagree more, and mainly because what we have to rely on, or what I rely on, is on the fine-grained sills in the floor of the complex that everybody, including James Brennan a moment ago, told us they are consistent. They can explain the crystallization sequences that we see in the Bushveld complex, in the crystal piles, and they tend to be fine-grained. There is no evidence of them containing cumulus chromite, supercotectic chromite, or in fact supercotectic sulfide or PG. We have studied 50 of them or so, analyzed them, characterized them, and you know, in lack of anything else, we have to assume that these represent the parent magmas. You could, of course, argue, well, you know, they could be unrepresentative. But as long as we don't have anything else, I think that's what I'm relying on. And these are fine-grained. They represent magnesium basalts, 12-13% MgO, perfectly normal magnesium-rich basalts. So I feel these magmas come in as largely as liquids rather than as slurries. And the formation of the seams happens once these magmas, you know, reach their liquidus and precipitate pyroxene, olivine, and chromite. And then we have granular flow separating these phases to produce a layering. That's what I'm at the moment, you know, assume is workable, is feasible.
Well, have you thought potentially that the B liquids and B1, B2, B3 liquids in the Bushveld are not parental, but are actually extruding out of the Bushveld?
So
in other words, they are a sill phase that is injecting outwards from the Bushveld rather than being parental magmas that somehow lurk around the sides and then come in.
Yeah, I think, yes, that of course is a possibility. So I think actually Yao and James Mangel, they investigated this possibility, whether the sills represent simply the fractionated ejections from the main chamber. Well, again, as I would argue, is, you know, we're using these magmas and they perfectly reproduce the crystallization sequences that we have in the intrusion. So that's one point why I would argue perhaps not. There was something else that there was another argument. I can't think of it now, but that would be perhaps, you know, I would immediately think of would be an argument against it, that they, so basically what they're saying is they're not representative of the cumulate sequence. And I think, you know, the evidence we have is that they can perfectly reproduce the crystallization sequences. There was somebody also in the back.
Yes, okay. Thank you. So maybe I cannot catch something from your model, but why these stringers chromite, which are on the boundary between pyroxenite 3 and lithiumite, are so thin compared to the gold from a background?
So You know, I mean, when you look at the field evidence, actually, then where is it? Here, then the pure anorthosite is actually also quite thin, it seems. So one could argue that the partial melting of the leuconorite, certainly in this case, was relatively minor, and so we produce only a small amount of aluminium saturated melt that could mix with the B1 magma and produce the chromitite.
The boundary with seal and pyroxenite, the partial melting was quite more intense. Yeah?
You mean with the upper boundary then, this one? The lower?
There's a chromatite in your lower boundary.
Yeah, that's a very thin one here, this
Yes.
one. Oh, this one. So this chromitite is the MG2. That would precipitate by granular flow, concentrate by granular flow from that magma influx. But this is a very thin one here. That's this egg box shaped chromitite, couple of millimeters.
Yeah, a couple of things, I may. So first off, when you look at these rocks now, they're universally accumulate or heteroaccumulate rocks. It's almost no attractive. But so if you think about the rheology of the sort of model that you're proposing here, you want to flow slurries on length scales of maybe tens of kilometers, hundreds of kilometers.
No, not hundreds of kilometers. They're flowing towards the center of the basin, not all around.
So certainly tens of kilometers.
Possibly.
So
it's possible that these things flow into local potholes, large potholes. So we may only be talking about kilometers, but perhaps sometimes more.
Even kilometers. Well, let's agree on kilometers.
Yeah.
But for that to happen, you've got to have a pretty substantial melt proportion in soil.
Yeah.
Now, how much it depends on factors that we don't really understand, like to what extent you get shear thinning. But you've got to assume that there's going to be a bare minimum about 30%. And it's probably got to be a lot more to actually get a crystal slurry to flow into. So you've got an awful lot of liquid. Now you've shown one possibility where maybe the higher-ups could be liquid draining out, but the higher-ups are not.
It produces an anorthosite, not the chromitite.
I mean, for that to work, the higher-ups would have to be like 30% of the volume of intrusion. So the question is, the first question, where does all that liquid? How do you get it?
I have no idea. These are cumulus.
Well, exactly. That's the thing.
Yeah.
They're cumulus. So if you're replacing them as gravity flows, then they were replaced with a large proportion of liquid.
And that liquid
And that liquid now has to have gone.
Yeah.
Where does it go?
Sitting in the top of the magma chamber, erupted as lavas.
Well, how do you
It
get
doesn't
it? How
matter
do you
what
get it
type
out?
of feed
Yeah.
you use. You need about 10 times more liquid than we see in the Bushveld humus. I'm sure Bruce would go with that. 10 would be the minimum. So the liquid, no matter what model you use, has to be either gone into the center, erupted, or squeezed out the sides. Doesn't matter which model you use, you've got a liquid balance problem.
Oh, okay, sure. No, granted that, but it's a very different problem separating crystals from liquid at the top of the crystal. That's easy. Convection, crystal center, any one of a number of mechanisms. But when you've buried, these things which you want to intrude deep into the crystal.
Yeah.
When you've buried those in there, you've now got a semi-solid rock above and below.
Yeah.
But presumably, I guess you would have to argue that the way you get that liquid out is by compacting the entire crystal pile and draining the liquid up. The sort of process that John was talking about yesterday. Is that how you see it happening?
Yes, yeah. So you touch on a little bit of a sore point there. So when you look at this contact here between the pseudo-reef and the overlying rocks, it's all ultramafic. If these things came in as sills, of B1 magma, they may produce a lot of olivine and pyroxene and some chromite. And the magma will continue to flow through this sill and so allow us to thicken the cumulate more and more. But in the end, you should see some highly evolved residual liquid. And certainly here we don't see that, right? Where is the granite? The little bits of granite, highly enriched in mica, for example.
Well, I'm not sure that's necessarily right. I mean, if that's starting out as a slurry, then you're draining the liquid out of it. The composition of that liquid is buffered by the composition of the phase that leaves behind.
Exactly.
So it's not going to be a highly evolved.
Yeah. So a little bit of
it's going to be a liquid in equilibrium with those cumulus phases.
Yeah, but a little bit of you know, relatively largely evolved liquid should be there and it's not there. And as you just said, we have to assume then, we have to argue that it's been draining outwards, upwards perhaps, up the magmatic bedding, into the marginal portions of the inclusion.
And you can continue over lunch or during the discussion. Next one is Brian. Thank you. Thank you all. So just last talk before the lunch.
Hi, everyone. Pleasure to be here. So I'm going to synthesize some field and petrographic observations, some geochemical data that my students and I and other colleagues have been gathering on the rum chromitites for a number of years now. And my aim here really is to just highlight the possibility, raise the possibility that reaction type formation processes are important in the formation of chromitite. So a distinction has been drawn in the literature between massive chromitite seams and relatively thin millimeter to centimeter thick seams, such as Merensky and such as we can see in this field photograph here, a few millimeters thick. And I'm not going to get into that distinction too much other than to say that it's the latter type, these millimeter to centimeter thick seams, that I'm mostly interested in here. Now, what do I mean by reaction? Processes are probably quite numerous, but one simple way of doing it is shown here on this binary phase diagram on the right-hand side, where we've got forsterite over here versus a northite over here on the right, and essentially contamination of a liquid that's crystallizing olivine by a relatively feldspathic cumulate can shift the hybrid either to something that is superheated with respect to olivine and then goes on to crystallize spinel plus liquid, or shifted even further over between A dash and B. So we've got the spinel only field here and a northite spinel and liquid over there. So there's different ways of doing this, but this is one that I think works reasonably well for the chromitite seams I'm about to talk about. And before I go on, it's worth pointing out as well that chromitite formation by reaction, by melt rock reaction, by melt percolation, is not universally accepted, but it's pretty common interpretation for chromitites formed in the lower crust and mantle sections of ophiolites. Much more so, I would say, than for layered intrusions. So quick context, I guess. Rum is a 60 million year old layered intrusion associated with opening of the North Atlantic. It's part of the British Paleogene, British and Irish Paleogene igneous province. And it's located in northwest Scotland here, and is part of the same magmatic activity, I guess, that is associated with the hotspot sitting under Iceland today. The intrusion itself, over here, this is rum. The intrusion itself is divided into three portions: the eastern layered intrusion, the structurally lower western layered intrusion, and this central intrusion in the middle. And it's subvolcanic. It was emplaced at about 2 kilometers depth or so. The schematic cross-section here showing these different portions of the intrusion, really just showing the nice layering in the eastern layered intrusion here, and this central intrusion, or central series as it used to be called, is interpreted as the fault zone, feeder zone, through which the intrusion was fed, and ultimately through which everything went back down once the magmastatic pressure waned. The eastern layered intrusion is by far the best and most well studied. By far the Most papers have been written on this part of the intrusion here. And it's composed of 16 macrorhythmic units. Each of those units has a periditic base and a feldspathic cumulate top. And each of those is supposed to have been formed by influx of a batch of magma and subsequent fractionation. And these layers, these macrorhythmic units are nicely picked out. Hopefully I'll get to show some of you these rocks later in the week, but nicely picked out by these terraces you see on the sides of the hills. So I'm going to talk a lot about proctolite, anorthosite, and peridotite. That's why I put this lithologic ternary up here. And when I talk about peridotite with respect to rum, it's not really peridotite, it's more like melatroctolite. So just worth bearing that in mind if the field photographs look like we've got a lot of feldspar in there. So I'm going to talk about two different types of chromitite seam. One forms at the unit boundaries, particularly in the eastern layered intrusion. So forms at lithological contacts or associated with lithological contacts, contacts between these units. Okay. The other type is formed within peridotite bodies, both in the eastern layered intrusion, also in the western layered intrusion and central intrusion. So those are two types that I'm going to now discuss in turn. So the unit boundary chromites are well known from not all unit boundaries through the eastern layered intrusion, but certainly at the boundary between unit 7-8 and 11-12, they're well known, for example. And to give you a feel for the geological context, here we've got 11-12, the 11-12 boundary. So this is the top of unit 11 with our troctolitic and anorthositic cumulate, and our new batch, if you like, of peridotite coming in on top of that. This is unit 12 here now. And right at the boundary is where we get these chromitite seams. This hand specimen down here shows it quite nicely. This is actually from unit 7-8, but this is very typical. So we get a 2 millimeter thick or so chromitite seam right at the boundary. We typically get a package of anorthosite right below that. And often we have one of these subsidiary seams, quite diffuse things separating anorthosite from troctolite below. We can also get supra seams, seams that sort of bifurcate up off the main seams into the peridotite. When we look at the boundaries of these things in the field, they follow the complex topography of the footwall rocks around all of these undulations, dips, and even overhangs, often without changing thickness at all. So a 2 millimeter thick seam will follow all of that complexity without really changing thickness. So I think a good argument there for in situ crystallization of some sort. And then also on the top right here, what I'm showing here is the unit 7-8 boundary a few hundred kilometers to the south. So down here, and the point I'm trying to make is actually while these seams are laterally continuous over hundreds of meters, they don't faithfully track the unit boundaries all the way around. They're discontinuous and more distal to what we think the source of the magmas might have been here in the central intrusion. They're absent, and we just get peridotite sitting on top of troctolite. There's some quite wonderful small-scale structure associated with these. This is the unit 7-8 boundary. On the top left, looking in plan view, you've got these little dimples of peridotite, which goes down into the anorthositic rock, and chromitite between both lithologies. This is a hand specimen view of that. These slump-type structures forming where you've got quite a significant increase in the volume of chromitite crystallized compared to sort of the normal seam thickness, and even evidence of some of these things breaking off. This is a thin section composite image of this structure here. one of the interesting things to note is that within the structure itself, you have intercumulus olivine. So really, chromite is the only liquidus phase crystallizing, the only cumulus phase crystallizing within this structure. But once we get out of it, we've got cumulus olivine, which interestingly, you can just about pick out the long axes are oriented parallel to the sidewalls of that structure. And I've wondered for some time whether these might not be analogous to the much larger pothole structures we sometimes see in the Bushveld. I can't see any reason why these things shouldn't be should be scale controlled. Some more small scale structure from the unit 7 anorthosite, so just a few centimeters below the unit 7-8 main seam. And here we get these thin apophyses, I guess, of peridotite intruding or forming within anorthosite. And what's really cool about them is that they've got thin chromite seams all the way around them. There's another one here that's a bit sharper. In this case, the peridotite actually dies away, and this is now just a chromitite seam here. These two faces are from the same hand specimen, just cut in half. And this is a thin section image of this area here in red. And what's again really interesting is that the olivine crystals forming this peridotite apophysis are quite coarse grained. Okay, so quite large olivine crystals for a relatively small peridotite body. Plagioclase in here is ubiquitously compositionally zoned. And take note, if you will, of these embayments that chrome spinel forms against olivine. These are ubiquitous throughout RUM, both in the unit boundary seams, but also in the intra peridotite seams as well. And I'm just showing this image here to give a flavor for more of the complexity. Sometimes anorthosite almost dies away, and we get these fragments of anorthositic material instead. So it dies away as a coherent unit. And we get these lenses and fragments of anorthosite that are completely rimmed by chromitite. And yeah, just a little bit of petrography. This is unit 11-12 now, looking at it in reflected light, just to make the point that there's quite a bit of sulfide in these things, and they are relatively PGE enriched. So these 2 millimeter thick seams have on the order of ppm levels of platinum and palladium, which is pretty significant when you think of the thickness of the seams. The image over on the right here is a ChemScan image, actually of the subsidiary seam, so sitting down a bit lower. So this is way up, and this is the anorthosite, and we see quite considerable or significant compositional zoning there of plagioclase, of those cumulus plagioclase crystals in the anorthosite, with relatively calcic plagioclase shown by the light blue and more sodic plag in the darker blue. The AN content variation there, I think, is on the order of about 15%. Yeah, just a close up then in this area here, showing how some of these sulfides occur. I'm not going to say a lot about those, other than to note that they show this relationship where they're almost ubiquitously stuck onto the sides of chromite crystals. So just a little bit of geochemistry now. We're sticking with these unit boundary seams. So I'm just going to whiz you through a few geochemical characteristics of them before I move on to the intraperidotite seams. So first up, we've done a little bit of osmium isotope work on these. There's quite a bit going on this diagram here, but let's just focus on the chromite seams across 11-12 up here, and unit 7-8 here with its attendant subsidiary seam. And the key things to pick out of all of this, these data here, first of all, the osmium concentration in parts per billion tracks quite faithfully with chromite mode percent. Okay, so that's the squares and the diamonds. So you see that the seams show sharp upticks in both osmium concentration and chromite mode, as you expect them to. The second thing is that the osmium isotope composition, represented here by gamma osmium, is relatively uniform right through the whole package, suggesting that these things are genetically related to one another. So anorthosite, troctolite, anorthosite, both seams, and peridotite all have the same osmium isotope composition. That's true more or less, certainly for 7-8 and pretty much for 11-12. And what's also interesting is that osmium isotope composition in both cases is more radiogenic than the composition of what we think the parental melt is, just shown down here. Okay. I'll come back to that in a second. And this is just to make the point over here, because we're supposed to be linking chromite seams to PGE mineralization a little bit, that we can pretty much show, allowing for some different flavors of platinum group minerals to be in there, that the base metal sulfides are where all of the PGE are cited. Okay, so we're looking at laser ablation data here for some sulfides from unit 7-8, and they more than satisfactorily account for the bulk rock budgets in these chromatites of the PGE. Okay, so moving on then from one of the most refractory elements in the periodic table to some quite volatile elements. We've done some halogen work on these rocks as well. And halogens are particularly useful as tracers of fluid provenance and crustal sources or crustal input. And so I can talk about the technique after if you're interested in, but we're able to measure relatively precisely the abundances of some of these low abundance halogens like iodine and bromine. And the key take-home points here, particularly for iodine, are that the chromite seams shown here in black squares are remarkably enriched in iodine, okay, up to 100 parts per billion, as enriched as one or two of the pegmatites we see, and definitely more enriched than most of the other cumulate rocks on RUM. That's particularly well borne out when we look at a ratio plot of iodine chlorine versus bromine chlorine. And we can see in this case now that the chromatites, these ones are from 7-8, stand all the way out here on their own with respect to everything else. Morb is down here, subcontinental lithospheric mantle over here, continental crust. So these things are remarkably enriched in iodine. It's an open question where this iodine is cited in these materials. We certainly have remnants of hydrous phases in some of the cumulates that would do it, and the chromite seams themselves, as with many other chromite seams from layered intrusions and ophiolites, show these rounded inclusions that sometimes contain amphiboles and biotite. So that's a possible candidate for hosting these heavy halogens as well. Noble gas isotope plot just says the same sort of thing. Our chromites have compositions that look a bit like or plot well into the marine sedimentary field. I'm showing you the same sort of data here, except against the same plot I showed you for osmium isotopes a little while ago, and just making the point again that these chromites, particularly for iodine, are quite enriched. Now, crustal reservoirs that are relatively enriched in iodine are quite uncommon. Okay? The only one really that works are biogenic sediments. Okay? So things like mudstones, for example. And so that could be what we're looking at here, cryptic evidence for some sort of crustal component in these unit boundary chromites. Somehow we're fractionating that iodine during whatever our chromatite forming event is. We have the right kind of sediments on RUM as well, Mesozoic mudstones, so that works in theory. And final slide then for these unit boundary seams, just showing you some argon isotope data. What I'm showing is a range of predicted. I've lost my mouse. No, I haven't. A range of predicted compositions for argon ingrowth for different ages of these are all country rocks we have closely associated with the rum intrusion, Mesozoic sediments, Proterozoic, Archean gneisses, and showing predicted compositions for varying potassium, the parent isotope, for our different possible assimilants. And given the age of rum, in the green squares here, this is what we should get. The white circles are what we do get. This is excess argon, okay? And so we almost certainly have to have input from some of these relatively old crustal components to explain our argon isotopes. So what does all that mean? So summing up, I guess, a little bit, these unit boundary seams, I think the field evidence, some petrography, so on, shows that they crystallized in situ. I think there's definitely evidence in there too for crustal components, different crustal components, whatever is happening during chromatite formation, they are interacting with something that's donating crustal signatures from multiple possible sources. Okay, we can come back to that again towards the end, but I'm going to move on now to our intra-peridotite chromatite seams. And these are abundant in particular in the western layered intrusion over here, and also to a certain extent in the eastern layered intrusion. They're associated with a rock called harrisite, which is not strictly unique to rum, but certainly type locality. Harrisite is a plutonic, it's kind of like a plutonic variant of spinifex textured chromatiite, where we get skeletal olivine grains. Some of these things can be up to meters in length, growing as a result of relatively deep undercooling of picritic melts on entry into the rum magma chamber. And that works because at least some of the parental melts feeding the rum chamber were picritic. So I'm going to show you an example we studied in some detail from the Unit 10 peridotite here. So this is Unit 10 with its relatively thick peridotitic base and trochlitic top. And my student did quite a bit of work logging this section in detail. See different parts of that log here, and all of these little black lines with circles, they all represent chromatite seams, these intraperidotite chromatite seams. So these things are quite abundant through the Unit 10 sequence. I would say up to hundreds of them. And they take different forms. They can be relatively sharp, like this one down here on the bottom right. So you can see it's got quite sharp contacts against the peridotite above and below, or they can be more diffuse, forming this chain texture where the chromite is situated in plagioclase and forms a network around the cumulus olivine crystals. This QuemScan image shows that often these seams have a nice grain size change of olivine associated with them. So going from one side to another, the olivine grain size can change quite significantly. Olivine shown in the yellow here, green is CPX, blue is plage, black is chromatite, obviously, and purple are later alteration of some sort. So one of the things that we noticed when we looked at these intraperidotite seams, particularly in Unit 10, was that the intercumulus plage tended to be optically zoned. Okay, so we noticed this is compositional zoning, and we thought it was more closely spatially associated with these seams than when we moved away from the seams above or below. And so we did a little bit more work. This is now from work my student did in 2019, 2020 or so, and found that some of the zoning was really quite spectacular. So this is a sodium map. This is a sodium map too. So we're looking at nice oscillatory zoning here in this plagioclase. Big black crystals here are olivine. These are little chrome spinels. And much more complex zoning going on here in the intercumulus plagioclase in this image. And so these are plagioclase crystals, intercumulus plagioclase crystals from within the area of this seam here. So we decided to try to do some strontium isotope work by micro drilling the different portions of the zones in these crystals. And so we did that and analyzed them for their strontium isotope composition, and we did some CPXs while we were at it. And we found that there was actually resolvable differences, resolvable heterogeneity in the intercumulus plage within these seams. And also within CPX, okay? You can see different optical, different chemical zones in this CPX crystal here. This is an aluminium map. And so we drilled these based on their aluminium composition. And for the CPX too, found that these things are all within uncertainty, different to one another in terms of their strontium isotope composition. So that's a pretty interesting result, and mapped out over all of the crystals we looked at. You can see them here. Sorry if this goes away. So at the different levels we looked at, the different symbols at each level are an individual crystal. So the green squares here all belong to one CPX, blue circles to one plage. This is not a chromatite seam, but these three guys here are all chromatite seams. And the bars here are previous, the colored bars, and the two gray bars are previous strontium isotope work from RUM. So we found within a few crystals quite a significant range in heterogeneity, spanning almost but not quite what had been done before for the whole of the Unit 10 package, but at the crystal scale. And so the really interesting thing about that, the important point there is that these crystals are intercumulus. Okay, and so to record isotopically distinct strontium in intercumulus crystals means that our crystal mush must have been an open system. Okay, and the conceptual model, I guess, that we developed to explain all of that was that we had these melt through flow or melt percolation zones that happened at a relatively late stage in the crystal mush, but that these things were responsible for these intraperidotite chromatite seam formation as well. And the other thing we can do from that sort of observation, heterogeneity preserved at that sort of scale, is say something about cooling rates. These things, when we do the calculations, must have cooled within tens to hundreds of years. So quite short timescale events. Okay, so I think that's all I wanted to say. There's still plenty to be done on these things. I think looking for some of these small scale isotopic variations in the unit boundary seams is worth doing as well. But whilst I haven't completely made up my mind, I think that probably those are reaction rates. So thank you very much for your attention.
Brian, you mentioned, maybe I mentioned that we will come back to these 2 points which were missing in Bushveld isotopes, more diagenic. So maybe that's what's the explanation.
Can you remind me what in particular? Sorry.
You told that you will come back to these couple of points which are more diagenic in sense of Bushveld.
Yeah, okay. So, well, I don't know if this is what I meant to say, but one thing I can say in addition there is one of the nice things about them is we have these different, because of the level, the intrusions placed out, we have multiple crustal contaminants, all of different flavors. Now, within our peridotite and within the intrusion itself, country rock blocks, cluster blocks are relatively rare. Okay? And so one of the things I've wondered about for a while is how do you generate these cluster signatures? And one way to do it is if that range of isotopic heterogeneity actually existed in the cumulate that's being assimilated already. And so that's what I think is important there, not just for isotopic systems like strontium and osmium, but also for halogens. So for example, suppose we're assimilating magnetite. We do have a lot of pegmatites sitting at the tops of some of the units in RAM, and all of a sudden then, not only can we explain our halogens, but we get into some sorts of things that James Bernard was talking about, the availability of water. Some of the pegmatites have got lots and lots of water in them. So if we're assimilating pegmatite, lots of people will go there too. I don't know if that's what I meant to come back to, but I hope that.
We asked you to talk about reactional chromites. You indeed showed us some, but you never actually told us what the reaction was you thought was happening. Could you elaborate, please?
Yeah, I sort of sketched it out in the second slide. I think it's probably reaction of dendritic counts with Feldspath. I think that there's variance on that. One of the problems is that you always see what the reactant is, and that's why I'm making that point about pegmatite. So on RUM, where we don't have it seems, tops of the units often have gabbroid rocks and pegmatite rocks. Where we do, it seems, those are absent. Let's go north side of Australia.
So you're going to melt the gabbro?
Possibly peg. Okay.
You're next. Just a quick question. If you see amoeboidal chromites in your reaction, you see the inclusion, are they very irregular in shape?
Yeah, they're there. Amoeboidal chromites, where we can see. They occur elsewhere, but they're not dominant.
Yeah, so you mentioned that the depth of crystal is only 2 kilometers. How did you estimate that? Do you use some barometers or just some like a estimate?
Good question. There's some metamorphic work from Marian Holmes on some of the intrusions, some of the satellite intrusions associated with the main intrusion. So around the edges, she's looked at some of the permeability, some of the metamorphic phases formed, and come up with about 2 kilometers. I think that's the best evidence. Having said that, we have all of the remnants of the volcano preserved around the margins, including eruptives, other breccias, everything else. So we know it was pretty shallow. And I've heard some people even suggest that it might be put into a lava. Maybe it's shallow as that.
Just one question, please, about the isotopes. You thought about the gamma osmium, and what is the amount of the gamma osmium difference between the magma or fluid margin and the chromites? And the second question is about the strontium. If you did some correlation between calcium amount in the blood phase and by comparison with the more radiogenic or less radiogenic signatures.
Let me answer the first one first. Not huge, but resolvable. I can show you the papers. It'll be beyond the third or fourth significant figure. What was the second question?
Regarding the calcium amount, because it's the zoned. So you micro drill the zoned logically.
Yeah.
So and you have the correlation with the more radiogenic with more calcium rich or
That's right. Yes. So the more radiogenic strontium tends to be associated with more anorthic patch. Certainly the chrome is associated with more anorthic. The relationship with strontium isotope composition is not strong, but if it's anything, it's
Or calculate.
more radiogenic.
Yeah, and that's might be, for example, fluids with some carbonates that bring the sedimentary rocks or something like that. It's just like
Yeah, there is carbonate, but that's
very
all.
little one because
Yeah, these are small variations.
Okay.
So I wouldn't like to go as far as, so where I see something like the iodine signal that I see, so clearly associated with there, I can say, right, there's something there, but and while there is carbonate, in the country rocks associated with them, I would expect that to be stronger.
Last question, then we get off for lunch.
Brian, just to get back to this relationship between these reaction chromatites and potentially one that came straight out of a magma. If you look at the Mariinsky, the bottom chromatite is sort of sitting along the base. That looks clearly a reaction chromite. It's incredibly low in any kind of PGMs. Whereas the chromatite that is sort of more disseminated thing, a little bit higher up, it can be about sort of up to sort of that type of thickness.